Like I have indicated, I am Mr. Mutlengwa, and we are going to go through counting principles together. Counting principles are the rules to find the total number of ways. Can we please mute the mics? Can we please mute the mics? Thank you very much. Counting principles are the rules to find the total number of ways. Things can happen or be arranged. The rules that we use under counting principles, the first one would be our product rule. To find the total number of ways things can happen or be arranged. Can we please mute the mics? Can we please mute the mics? Thank you very much. Like I was saying, counting principles are the rules that are used to find the total number of ways things can happen or be arranged. Those rules involve rule number one, which would be referred to as the product rule, that says if event one has m ways of happening and event two has n ways of happening, therefore both events can happen in m multiplied by n ways. If event one has n ways of happening and event two has n ways of happening, therefore both events can happen in m multiplied by n ways. For example, for this first rule, the product rule, if I have 3 shirts and 4 pens, therefore event one is 3 shirts, event two is 4 pens. The total number of outfits that can be made using those shirts and pens would be 3 multiplied by 4 ways, which is 12 ways. Therefore, if one has 3 shirts and 4 pens, the total number of outfits that can be made by those 2 items would be 12 outfits. This would be the first rule that we have, which would be referred to as the product rule. And then from our product rule, we then have our factorial notation. We have the factorial notation. Factorial notation, whereby factorial is now referred to as the product of the descending natural numbers from n to 1. Product of descending natural numbers from n to 1, that would be referred to as the factorial. For example, 5 factorial refers to 5 multiplied by 4 multiplied by 3 multiplied by 2 multiplied by 1. For it to be referred to as a factorial, it has to be the product of those descending natural numbers, and they'll have to start from n up until they get to positive 1. Product of descending natural numbers from n until they get to 1. In that case, then we'll refer to that as our factorial. Now, factorial on our because that factorial will be in grade 12. You press shift on your calculator and then that button just below mode. If we are using the same calculator, that exclamation on the calculator there, that is our factorial. For example, one might say 8 factorial would be 40,020. By pressing 8 shift and then that exclamation mark, you would be having your factorial. Now, for it to be referred to as a factorial, it has to be the product of descending natural numbers and descend from n until they get to 1. If they did not get to 1, then it can be referred to as a factorial. Now let's check the examples that would be involving factorial and the ones that are not involving our factorial. Okay, I think I'll have this as our first example. that says arrangement of objects would be our first example. The total number of objects that we have in this case, we have 8 fruits, if I counted them correctly. We have 8 fruits here, and then it says, the first example says, determine how many ways can all the fruits be arranged in a row. Now, when it comes to the arrangement of objects, the number of objects that we have would give us the number of spaces that you are going to create, because it becomes much easier if one creates the spaces for the objects that are given. The number of objects that we have would give us the number of objects that we are going to have. For example, here we have fruits, and those fruits are 8. Therefore, we are going to create for the first one, letter A, example 1. We are going to have 8 spaces. 1, 2, 3, 4, 5, 6, 7, 6. 1, 2, 3, 4, 5, 6, 7, 8. We are going to arrange 8 fruits in a row. Therefore, we are going to need 8 spaces in that row. Now, all the 8 fruits would be competing for the first position, meaning any of the 8 fruits, it can be a banana, it can be a pineapple, it can be an apple, it can be an orange that occupies the first position. Therefore, on the first space, we are going to write 8. 8 does not mean all 8 of those fruits would occupy the first position. The 8 that is written on the first position means 8 fruits are competing for that first position there. Hence, we are writing 8. But one of the 8 fruits occupies this. It leaves us with 7 fruits. Therefore, the second position, only 7 fruits would be competing there. One of the 7 occupies that. Then we have 6 fruits that are competing for the second position. And then the fourth position, we are only going to be left with 5 fruits. And then that other position will be left with 4, 3, 2, 1. And if we check this is a product of natural numbers, descending natural numbers from n to 1. Product of descending natural numbers from n, they descend until they get to 1. Therefore, this would be n factorial, because these natural numbers are descending from n to 1. Therefore, this is 8 factorial. And then when you punch 8 factorial on your calculator, you would press 8 and then shift and then that exclamation mark below the mode button. After punching that on your calculator, 8 factorial would give us 40,320. Therefore, these 8 fruits can be arranged in 40,320 ways in a row. Now, this is where factorial is, or this is what factorial means when you have the product of descending natural numbers from n up to 1. Let's check the second example that we have. The second example says now, determining how many distinct ways can 4 of the fruits be arranged in a row. We no longer arrange all of them in a row, whereby now we have 8 fruits. We now, in the second example, only arranging 4 in a row. 4 fruits in a row. That means the number of items that we are going to have. We have 4 fruits. Therefore, the number of spaces there, we will be opening 4 spaces instead of 8. Because on example number 1, we opened 8 spaces because we are arranging all the fruits, all of them in a row. For the second example that we have, only 4 fruits are arranged in a row. Therefore, we are going to open only 4 spaces, 1, 2, 3, and 4. Now, if we have 4 spaces that are arranged in a row, how many items or how many fruits would be competing for the first position? Oh, this is letter A, and then this would be letter B. The number of fruits that are competing for the first position would be all 8 of them. any of the 8 can occupy the first position. And then from there, one of the 8 occupies that. We are left with 7 fruits. Therefore, the second position, only 7 fruits would be competing there. And then let me write it properly. Here, only 7 fruits are competing. After the 7 fruits that are competing for the second position, meaning that 2 fruits would have occupied, one would occupy the first position, then the second fruit would occupy the second position. That means we are left with 6 fruits that would compete. Any of the 6 can occupy the third position. After any of the 6 occupies the third position, we would be left with only 5 that would compete for the last position. Therefore, you multiply this in between there, you are multiplying 8 multiplied by 7 multiplied by 6 multiplied by 5. Then this is not a factorial. Please be aware that letter A is a factorial because it starts from 8, it descends until it gets to 1. But the second one will not be referred to as 8 factorial because it is descending, yes, but it does not descend until it gets to 1. Therefore, the answer for this will just be 1,608. Can we please mute our mics? Thank you very much. Now, this is the first example of arrangements of objects, whereby now we are having a factorial, and in some instances, it won't be a factorial because it does not run until it gets to 1. Now, this is the first example that we have. Let's check the second example. Can we please mute our mics? Thank you very much. Okay, the second example that we have then. The second example that we have, there are, again, the items that we are arranging. This example says there are 7 shirts and 4 different pairs of trousers in a cupboard. The clothes have to be hung on the rail. Now, how many items or how many clothing items do we have in total in this example that we have? The total clothing items that we have 7 different shirts, or we have 4 different pairs of trousers. Therefore, the clothing items that we have in total here are 11. You add the 2, therefore you have 11 different types of clothing items here. Now, the first question then says, in how many different ways can the clothes be hung on a rail? All 11 of them. In how many different ways can those clothes be hung on a rail? I'm going to divide my screen into 2 so that I can respond on this other side. 1.1. All 11 of them are to be hung on a rail. Therefore, the number of spaces that one has to create, because we have 11 different objects or 11 different clothing items, then you will create 11 spaces. Therefore, for 1.1, you are going to create 11 spaces, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Now, with the 11 spaces that we have, all 11 items will be competing for the first position. Therefore, on the first space that we have, we are going to have 11 there. On the first position that we have, we are going to have 11 because all 11 of them will be competing for that position there. Now, one of the 11 clothing items occupies that position. That leaves us with 10 for the second position. One of the 10 occupies that. It leaves us with 9 that would compete for the third position. This will descend. After 9, we'll have 8, 7, 6, 5, 4, 3, 2, 3, 2, and 1. Therefore, this is the same as 11 factorial because this is the product. In between here, we multiply. This is the product of descending natural numbers from n. In this case, our n. In this case, our n is 11 because we are descending from 11 until we get to 1. Therefore, this is the same as 11 factorial. And you can punch 11 factorial on your calculator. It would give you a bigger sum. 39,916,800. But you can leave your answer as 11 factorial. It is still correct leaving it there. The second one, the second question that we have, those different items can be grouped together, and those different items, we can have the restrictions on positions, whereby now a certain position is restricted to only accommodate a particular clothing item, or the clothing items can also be grouped together. Now, when it comes to grouping and the restricted positions, you start first with the items that are grouped, and then you can move out after getting the items that are grouped. Usually, whenever there is a grouping that happens, we will say it is a group factorial. Whatever that is being grouped there, we will write it as group factorial. Then we multiply this by whatever the items that are left there. Group factorial multiplied by item factorial. Group factorial multiplied by item factorial. Now we check the second question when now we are doing grouping of the items. Now, the first question under grouping, it says, in how many different ways can the clothes be arranged if all the shirts are to be hang next to each other, meaning we are grouping the shirts. On that rail, there must be shirts only and next to each other, and the pairs of trousers are also to be hang next to each other, meaning in this case, we have two groups.
We can't hear you now, sir.
Sir, we don't see.
Ano ba na? Inferior.
It should be that way. I have to resume. According to
Beautiful.
Sorry for that. I think we had technical problems, network problems, but they are sorted now. We can continue with our presentation. Sorry for the inconvenience. We were on 1.2 on grouping different items that we have. We said it's much easier for us when we are approaching the question of grouping to say group factorial multiplied by item factorial. Group factorial multiplied by item factorial. We said here in how many different ways can the clothes be arranged if all the shirts are to be hanged together or next to each other and all the pairs of trousers are to be hanged next to each other on the rail as well. Now, in this case, we have two groups. We are grouping all the shirts and we are also grouping all the trousers. Based on the statement that we have, there are different shirts, 7 different shirts. If there are 7 different shirts, it means for the shirts, we are having 7 spaces. 1, 2, 1, 2, 3, 4, 5, 6, 7 for the different shades that we have. Meaning for the first one, all the shades would be competing for the first position. Hence, we are going to have here 7. That means all 7 of them will be competing for the first position. One of the 7 shades occupies that position. We are left with 6 shades, and then it will be descending like that. 7, 5, 6, 5, 4, 3, 2, 1. Meaning for the shades only, we have a group of 7 factorial. But this is not the only group that we have. We are also going to have a group of pairs of trousers where we are told that we have 4 different types of trousers. Then we have 4 spaces for the trousers. 1, 2, 3, 4, and then all 4 of them would be competing for the first position of trousers. One of the 4 occupies that. We are left with 3, and then there would be 2 and 1. Therefore, for the trousers, we have 4 factorial. And then for group factorial, then we have 2 groups. That is 7 factorial for the trousers. We multiply this with 4 factorial of 7 factorial for the shirts, 4 factorial for the trousers. Then we multiply it by the number of items that we have. We have 2 different types of items here. We are going to have the first group for the trousers and then the second group for the shirts. Therefore, this is item number 1 and this is item number 2. Therefore, 7 factorial by 4 factorial, we are going to multiply by 2 factorial. This 4 and 7.
Wat is al in het en die volgende is een koe met een kalf gemaakt met jou. En niet dan jou met een klaar.
Am I audible enough?
Sir, ha re bone screen, ha re bone.
Check again. Am I audible enough?
Yes, sir.
Thank you very much. Thank you very much. Is the screen sorted as well?
The screen is
Are we
not
able
sorted,
to see
sir.
the screen so that I can reshare?
No, sir.
Can you restart maybe on your side? I think I'm able to see this side. Thank you very much. I think we are sorted with the screen, and I am audible enough. Thank you very much. The 7
We are not
factorial
sorted on
and
the
4 factorial
screen.
are for the
Sir,
groups.
we are
Hello?
not sorted. We are not sorted on the screen.
Can you rejoin the meeting? Just exit the meeting and then rejoin the meeting, then it would be visible. Your screen will be sorted after doing that. I think I have sorted out the screen issue. If you are not able to see the screen, just exit the meeting and then rejoin the meeting again. Thank you very much.
Good.
Okay, and then the
Yeah.
4 factorial and the 7 factorial, this is the groups that we have. We have 2 groups there. We are grouping the trousers and we are also grouping the shirts. Then these 2 factorial is for the items that we have. After grouping them, we now have 2 items. Then the response to that would be 7 factorial multiplied by 4 factorial multiplied by 2 factorial. And you can be able to punch that in the calculator. It would give you the answer is 241,920, meaning those clothing items, if they are to be arranged on a rail and trousers are next to each other and shirts are next to each other, then they can be arranged in 241,920 ways. Now, let's check the third example that we have. Now, the third one would be the restricted positions, because when it comes to the items that are arranged, we must be able to respond to the grouping. We must also be able to respond to where restriction is taking place. And whenever a position is restricted, we start first filling in that position that is being restricted, and then we can go and fill other positions. Let's check the third question or the third example that we have. The third example says, in how many ways can a pair of trousers hang at the beginning of the rail and a shirt will be hung at the end of the rail? Meaning there are 2 positions that are restricted here. The first position that is being restricted here is the first position. The first position being 11 items that we have. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Now we have 11 clothing items. Now the first position, it must begin. What is beginning there? The trouser. The trouser must be hung at the beginning, meaning only trousers are going to compete for the first position. And the last position must be a shirt, meaning on the last position that we have here, it must only be a shirt that is competing there. Now let's check. We start first filling these restricted positions before filling in any other position. the number of shades that we have, or the number of trousers that we have four different types of trousers. Because it is said that we have different pairs of trousers. If trousers are hanging at the beginning, meaning only 4 trousers will be competing for that position. And then the last position must be a shirt, because we have 7 different types of shirts. Then on the last position, any of the 7 shirts can compete for that position. The 7 and the 4 does not mean all 4 of them would occupy that first position. It means all 4 of them are competing for that position, but only one would occupy that. Meaning, of the 11 clothing items that we have, 1 is going to occupy the last position, 1 is going to occupy the last position, meaning of the 11, we subtract 2. That means we are left with 9 items now, because 1 shirt would have occupied the last position, 1 trouser would have occupied the first position. Now we can then fill the unrestricted positions after. After filling the restricted positions, then we go to this unrestricted positions. Now the number of clothing items that are remaining would be competing for this position here, meaning all 9 of them would compete for that position. And then 1 of the 9 occupies there, we are left with 8 clothing items, and then it would be 7, 6, 5, 4, 3, 2, 1. Remember what we said about factorial. We said a factorial is the product of descending natural numbers from n up to 1. Now, meaning this part becomes our 9 factorial, because it descends from 9 until it gets to 1. Therefore, our response to the third question would be 4 multiplied by 9 factorial multiplied by 7. 4 multiplied by 9 factorial multiplied by 7. 4 and 7 are not factorials. Only 9 is a factorial in this instance. 4 and 7 do not descend from 4 up to 1. Even 7 is also not a factorial. It is just 7 as it is. Factorial has to be the product of descending natural numbers from n until they get to 1. Therefore, you multiply this and then it will give you the bigger sum as well. 10,160,000. It would give you that bigger sum, 10,160,640. Meaning, if now we have a shirt that is going to start, or trouser that is going to start, and then a shirt at the end of that range. Therefore, we can rearrange those different clothing items in 10,160,640. Now, let's check the other examples then. From there, we have seating arrangement, where now we are going to deal with people that are going to be sitting in a row. Again, on the seating arrangements, can we sign the register as for so long? The registers has been sent in the subject advisors group. The attendance registers are sent in the groups, WhatsApp groups. Can we please attach our signatures to those registers? Thank you very much. Now, when it comes to seating arrangements, these are the 4 bullets that we have for seating arrangements, whereby now we still have the restricted positions on the seating arrangements, where a particular learner would prefer to sit in the middle of the row, or a particular learner would prefer to sit at the end of a row. We also have grouping in this case, but in this case, that grouping would be referred to as them sitting next to each other or them sitting together. If 2 particular learners prefer to sit together, then we refer to that as grouping. The same way as we responded to the question of grouping under objects. That is the same way as we are going to respond to this question of sitting together. The third one, we can also have two particular learners that would refuse to sit together. And then we can also have them sitting in alternating positions. Alternating positions, meaning if we have two different genders, for them to alternate, it would be having to be a boy, girl, boy, girl, boy, girl, boy, girl, and so on. That is them sitting in alternating positions. Now let's check the examples that we have under this seating arrangements. Now I have an example here. It says, determine the number of distinct ways 3 boys and 2 girls can be seated in a row if I have 6 questions here. It says, number 1, there are no restrictions, meaning anyone can sit anywhere. Now, because we have 3 boys and 3 girls, or 3 boys and 2 girls, that means all in all, I have 5 kids, or 5 learners, if I may say. Then in how many ways can they sit? The number of chairs, like you see on my example, we have 5 different types of chairs, or we have 5 chairs. Now, for letter A, if we have 5 different people that are competing for 5 chairs, then the number of people or the number of chairs that they are competing for gives us the number of spaces that you are going to create. We are not creating spaces based on the number of people. We are creating spaces based on the number of chairs that are to be occupied by those people. Because there would be times when there are 5 people, but there are only 2 chairs to be competed for. So the number of people do not give us the number of spaces that we have, but the number of chairs that they are going to occupy gives us the number of spaces that you are going to create. Number 1, there are no restrictions. There are 5 of them. There are 5 chairs. Therefore, we open 5 spaces. 1, 2, 3, 4, 5. With my 5 spaces for letter E, with my 5 spaces, all 5 of them would be competing for the first position. All 5 of them would be competing for the first seat. Not all 5 of them occupy that seat. 1 of the 5 occupies the seat. It leaves us with 4 learners that are to compete for the second seat. Meaning here we are going to write 4. That 4 means there are 4 people that are competing for that seat. 1 of the 4 seats there, then we are left with 3, 2, and then there would be 1. 5, 4, 3, 2, and then we also have 1 here. Then this 5, 4, 3, 2, 1, it is the product of descending natural numbers because we multiply. Product of descending natural numbers from n to 1. Our n in this case is this 5 because they descend from 5 up to 1. Therefore, this is 5 factorial. Then you can punch 5 factorial on your calculator. It would give you your answer. 5 factorial on the calculator, it gives us 120, meaning they can sit in 120 ways. Letter B says the 2 genders must sit together. The 2 genders must sit together. If the 2 genders are sitting together, that means we are having 2 groups. I will have the group of boys and I'll also have the group of girls. Remember, I said it's much easier if we do it with group factorial. Group factorial multiplied by item factorial. Group factorial multiplied by item factorial. Our group factorial in this case would be the ones that we are grouping together. We are grouping 2 genders together. The first gender being the males, the second gender being the females. The first gender being the males, the second gender being the females. Now with groups in this case, we have 3 boys. Therefore, for them, it would be 3 factorial. They will sit in 3 factorial ways. And then we also have the girls. For the girls, they can sit, there are 2 girls, meaning they can sit in 2 factorial ways. After grouping the boys and the girls, the number of items that we have 2 items in this case. We have the boys, we have the girls. After grouping them, we treat them as one. That means I'll have 1 group of boys, 1 group of girls. Therefore, 3 factorial by 2 factorial. We are also going to multiply it by 2 factorial. Then our answer to that would be 3 factorial, 2 factorial by 2 factorial. That is the same as 24. Meaning, if both genders or if 2 genders must sit together, then they can only be able to sit in 24 different ways. Letter C, the boys must sit together. The difference between letter B and letter C is that on letter B, we are having 2 groups. But on letter C, we are only having 1 group because it is only the boys that are to sit together. Meaning on letter C, we are still going to have our group factorial multiplied by item factorial. But our group factorial in this case is the number of boys. For letter C, the boys that we have 3 boys. That means it will be 3 factorial for the boys. And then those group or that group, we now treat it as 1. It goes and joins the 2 girls. It will now become the 3rd item on the unused girls. Remember the girls, we did not group them. We are only grouping the boys. For the boys, it's 3 factorial. That means we are done with the first part. Group factorial, done. It is 3 factorial because we have 1 group. That 1 group goes and joins the 2 girls, meaning the group of boys as 1 plus the 2 girls. It becomes now 3. We now have 3 items. Then our answer would be 3 factorial multiplied by 3 factorial. 3 factorial multiplied by 3 factorial. That means if only the boys are grouped together, they can be able to sit in 36 different ways. 3 factorial multiplied by 3 factorial gives us 36. Now let's check letter D. Letter D says the boys and girls sit alternately, meaning that they are to alternate. Now, when it comes to alternating positions, you first check the total number of learners that you have. In this case, if I add 3 and 2, I have 5 learners. If the total number of learners is an odd number, then they can alternate only in 1 way. But if the total number of them is an even number, meaning that if you have 3 boys and 3 girls, for example, in this case, therefore there are 6 learners that you have there. For them to alternate, it would happen in 2 ways. If this is the case, then let's respond to this letter D. 5 spaces, 1, 2, 3, 4, 5. For them to alternate, the first position must be occupied by the group that has the higher number. If you check, the other one is 3, the other one is 2. Meaning for them to alternate, the first position must be a boy. It must be a boy that occupies that position, the boy that occupies that position, and the boy that occupies that position. In that way, they would alternate because in between the boys, there would be the girls. But if they are to start with a girl, they will not be alternating because the last 2 positions, it will be occupied by a boy. 1, 2, 3, 4, 5. If they start with a girl, it will be a girl, a boy, a girl, then you will not have another girl to compete for the last position. Then they will not be alternating because here it would be boy and boy. Therefore, this one, we are not doing it this way because they are not alternating if that's the case. Now, let's erase this. For them to alternate, because their total is an odd number. For them to alternate, they have to start with a boy. The number of boys that would compete for the first position would be 3. The number of boys that would compete for that other position that is being competed by boys is 2. The number of boys that would compete for the last one would be 1. That means for the boys only, we have 3 factorial because it is the product of descending natural numbers from 3 up to 1. And then the girls, we are only having 2 girls that will compete for this position. And then the last position would also be competed by only 1 girl. Now, if we check the girls as well, it is 2 multiplied by 1. 2 multiplied by 1, it is product of descending natural numbers. Therefore, it would be 2 factorial. Therefore, our response for letter D would be 3 factorial multiplied by 2 factorial. Multiplied by 1 because it can happen in one way if the total number is an odd number. If the total number was an even number, then you would multiply your response by 2 because that would happen in 2 ways. They can start with either a boy or girl. But in our case, it is just 3 factorial by 2 factorial. Let's check letter E. Letter E. Let me erase here for letter E. Okay, letter E. Letter E says the youngest boy and the girl must sit together. Meaning here, we are grouping 1 boy and a girl that must sit together. 1 boy and a girl, our group factorial. How many people or how many learners we are grouping? We are only grouping 2 learners. That means our group factorial for letter E would be 2 factorial. That 2 factorial is for the boy and the girl. 2 factorial for a boy and the girl. Then we treat that as 1. 1, 2, 3, 4, 5. We treat this as 1. We treat that 2 factorial as 1. This is our 2 factorial because both of them can compete. 2 of them can compete for this, either a boy or a girl that can occupy that. If 1 occupied that, only 1 is going to be left to compete for the last position. Then that becomes a product of descending natural numbers from n to 1. This then becomes our 2 factorial. That is our 2 factorial. Then from there, we check the number of items that we have. The number of items that we have would be, this is item number 1, that group. Item number 1, this is item number 2, item number 3, item number 4. That means after grouping them, we now have 4 items. Then for 4 items, we are going to have our 4 factorial. This is for the items. This here is for the group. And this here is for the items. And we said whenever we are dealing with groups, we are saying in response to that for letter E, it is group factorial. In our case, our group factorial is 2 factorial. Multiply it by item factorial. The number of items that we have is 4. Therefore, it's 2 factorial multiplied by 4 factorial. Then you can punch that in the calculator. 2 factorial by 4 factorial gives us 48. Meaning if the youngest boy and the girl must sit together, of these 5 learners that we have, then they can only be able to sit in 48 different ways. In 48 different ways. Let's check letter F. Letter F. Letter F. Letter F. Letter F reads as follows. Determine the number of distinct ways 3 boys and 2 girls can be seated in a row if one of the boys does not want to sit in the middle. Meaning there is a restriction here. There is a boy who does not want to sit in the middle of the row. Meaning of the 5 chairs that we want, there is a boy that does not want to sit in the middle. Now, before we want this does not, in how many ways can they sit without any restriction? In how many ways can they sit without a restriction? They can sit in 5 factorial ways. They can sit in 5 factorial ways without any restriction. They can sit in 5 factorial ways. And in the 5 factorial ways, there are 2 possibilities. In that 5 factorial ways, in the 120 ways that they can sit, there are 2 possibilities that we have there. Possibility number 1, in the 5 factorial. In the 5 factorial, there are 2 possibilities. Possibility number 1, there is a chance that that boy can sit in the middle. Let me erase this part. Meaning in the 5 factorial that we have 2 possibilities. I am going to write the possibilities here. Possibility number 1, there is a chance or there is a possibility that the boy will sit in the middle. There is a chance that the boy will sit in the middle, and there is also a chance of the boy that he will not sit in the middle. Meaning we have 2 possibilities in the 5 factorial. Our 5 factorial, because there is no restriction in the 5 factorial, anyone can sit anywhere. The boy that does not want to sit in the middle, there is a chance that that boy can sit in the middle. And again, in the 5 factorial ways, there is a chance that the boy does not sit in the middle. Now, in the 5 factorial, we are looking for these possibilities where the boy does not sit in the middle. This is what the question is looking for. Meaning, in the 5 factorial that we have, we are going to subtract this part where the boy sits in the middle. Because there are 2 possibilities. Either the boy sits in the middle or the boy does not sit in the middle. So for us, in the 5 factorial ways, of which that is 120 ways, we are only going to subtract the chances of the boy to sit in the middle. Then we'll be left with where the boy does not sit in the middle. Now let's check in how many ways can they sit if the boy sits in the middle, so that you can subtract it on our 5 factorial. Let me erase this part here. Okay, I think the space is enough. 1, 2, 3, 4, 5. We have 5 learners there. Now the boy, we want to subtract on 5 factorial. We want to subtract the chances of the boy sitting in the middle. That means here we have a boy, 1 boy that sits there. Meaning here would be just 1, because there's this 1 boy that we don't know that does not want to sit in the middle. We can even give the boy a name. We can say Thabo does not want to sit in the middle. Therefore, for us to have where Thabo does not sit in the middle, we'll first fix Thabo in the middle, meaning we would have 1 there. Thabo will not be sitting anywhere because we have fixed Thabo on the first position, meaning the first position or on the middle position. Here, there are 4 learners that are going to compete. 1 of the 4 occupies that, then we have 3 that are competing here. Because the middle position is fixed for that one learner. There is nothing that you can do to it. Remember, if we have restricted positions, we start first filling in the restricted position before filling in any other position. That means up to this far, 3 learners have occupied chairs. We are left with 1 or 2 and 1. This is the product of descending natural numbers. My descending natural numbers are 4, 3, 2, and 1. 4, 3, 2, 1. That gives us 4 factorial. Multiplied by 1. That does not make any difference in this case. But it's 4 factorial multiplied by 1, meaning that the number of ways they can sit where a boy sits in the middle is 4 factorial multiplied by 1. Now, for us to find where the boy does not sit in the middle, the boy does not sit, meaning this sit in the middle, we have it. Sit in the middle is 4 factorial by 1. 4 factorial by 1. Now, for us to be left with where the boy does not sit in the middle, our response would be that 5 factorial. Then we'll only subtract 4 factorial by 1. Then on those total number of ways, we would be left with where the boy does not sit in the middle. Meaning our response for letter E, where a boy refuses to sit in the middle, or the boy does not want to sit in the middle, our response to that would be 5 factorial. That is the total number of ways without any restriction. We minus the outcomes that we are not looking for. We do not want the boy to sit in the middle. Therefore, we subtract where the boy sits in the middle. 5 factorial minus 4 factorial. Then that will give you the answer. Punch this in the calculator. If you punch it in the calculator, it would give us 96, meaning they can only sit in 96 ways if a boy refuses to sit in the middle. I hope I was a bit slower on that, and I hope I made sense on that. Now let's move on to the next examples. Now, I have this example here. We can take 2 minutes to respond to it because it is the same as the one that I just did now. A Banana Airways aeroplane has 6 seats in each row. Can we respond to these 2 questions in, let's say, 4 minutes, 2 minutes each? Okay, thank you very much. I think 4 minutes has lapsed. We can check if we have responded to the two questions the same way. 1.1 says, how many possible arrangements are there for 6 people to sit in a row of 6 seats? Remember, we said the spaces that you are going to create are not based on the number of people, but based on the number of seats that the people are competing for. Because we can have 6 people and then we have 4 chairs, then we will create 4 spaces if that was the case. But in this case, we are having 6 people and 6 different chairs. That means the number of spaces that you are going to create for number 1.1 would be 6. 1, 2, 3, 4, 5, 6. Then let the people compete for the chairs starting from the first chair. The number of people that would be competing for this chair would be 6. Any of the 6 can occupy that. If one of the 6 people occupied that, it leaves us with 5 for the second chair. It leaves us with 4 there, 3, 2, and 1. Remember, we said product of descending natural numbers from n to 1. It is a factorial. Then if this is the case, you can be able to punch it on your calculator and have 6 factorial, because this is the product of descending natural numbers. They descend from n up to 1. Then it is 6 factorial. Then you punch your 6 factorial on the calculator. 6 factorial gives us 720, meaning this group of people can be able to sit in 720 ways in a row that has 6 chairs. The second question, 1.2. The second question, 1.2. 1.2 says, Toliswa and Anele and 4 other passengers sit in a certain row on Banana Airways flights. In how many different ways can these 6 passengers be seated? If Toliswa and Anele must sit next to each other, meaning we are grouping Toliswa and Anele because they want to sit next to each other. Then we go back to what I initially said when it comes to grouping. It is group factorial multiplied by item factorial. Our group in this case is Toliswa and Anele. There are 2 people in a group. That means it would be 2 factorial. Remember, there are 6 chairs. 1, 2, 3, 4, 5, 6. There are 2 people in this group. 2 of them would be competing for the first chair in the group. Then one of the 2 occupies that. Then the second chair would be left with 1 person competing for it. That is our group. This is where that 2 factorial is coming from this group. 2 factorial. Then it leaves us with this number of items. This would be item number 1. Item number 2, number 3, number 4, number 5. Therefore, the number of items that we have then would be 5. Then our response for the item would be 5 factorial. Remember, you only add 1 if the position is not fixed as well. If the position was fixed, then the items would be 4. Say, for instance, the question said, Toliswa and Anele must sit next to each other on the first 2 chairs. Meaning we are fixing their position. They are only competing for the first 2 chairs. Then the items would be 4. But if this is the case, Toliswa and Anele must just sit together anywhere on those 6 chairs. Then it increases the number of items from 4 to 5. Therefore, our response to letter or 1.2, our response is 2 factorial for the group multiplied by 5 factorial for the items. Then you can punch that on your calculator. 2 factorial multiplied by 5 factorial gives us 240, meaning Toliswa and Anele, if they are to sit next to each other, they can only do that in 240 ways if there are 4 other people that are with them. Now, after seating arrangements We can check the other examples of our counting principles. Arrangements of letters. Arrangements of letters. When it comes to the arrangements of letters, there are two types of words that we have. We have a word that has identical letters. We also have words with non-identical letters. And also on the letters, a position can be restricted to only accommodating a particular letter. A word starting with a W, a word ending with a Z, a word ending with, meaning there can be restricted positions on the arrangement of letters. And also there can be grouping on the arrangements of letters. In how many ways can the letters of the word arrangements be arranged if all the vowels are grouped together? Meaning on the arrangements of letters, there can be identical and non-identical, there can be grouping, and also there can be restricted positions. Let's check the examples that we have. Hopefully this example is clear enough. This is for the non-identical letters in a word, or a word that has no identical letters. A word that has no identical letters. It says here, how many ways can the letters of the word equations be arranged if? Now there is the restriction. The first letter must be an E. Now the number of letters in a word gives us the number of spaces that you are going to create. It works much easier if we create the spaces. Now, if we check this example, we have equations. Equations has 9 letters. Equations has 9 letters, meaning we are going to create 9 spaces for letter A. Letter A, then we are creating 9 spaces. 1, 2, 3, 4, 5, 6, 7, 8, 9. We have 9 spaces because the word equations has 9 letters, but the first letter must be an E. The first letter must be an E, meaning position 1, only an E must occupy that. Meaning position 1 would be 1, because E is not competing with any other letter. We start first filling in the restricted positions, then we can move to the unrestricted positions. E occupies the first position, meaning on the word equations, we scratch out E. We no longer have E on that word equations. We are now left with 8 letters. Because we are done with the restricted positions, we can now fill in the unrestricted positions. All 8 letters will be competing for the second position. One of the 8 occupies that, we are left with 7. One of the 7 occupies that, we are left with 6. Then it will be 6, 5, 4, 3, 2, and 1. Now we check the descending natural numbers. The product of descending natural numbers starts from 8. It descends from 8 up to 1, meaning my answer here would be 1 multiplied by 8 factorial. 1 multiplied by 8 factorial gives us 40,320, meaning if E starts the word, the letters of the word equations can be arranged in 40,320 ways. Now, the second example that we have. The second one says, the first letter must be an E, and the last letter must be an S. Now, there are 2 positions that are restricted now. The first letter and the second letter or last letter. First position, last positions are restricted. 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 spaces for 9 letters. Equations has 9 letters. They are saying the first position must be an E. The last position must be an S. Meaning here it is only an E that is going to compete there. The last position is also going to be 1 for an S. On the word equations, E is on the first position, S is on the last position. It leaves us with 7 letters because from the 9, 2 are engaged on the first and the last letter, meaning we are left with 7. The second position, only 7 letters are going to compete for this. The 7 letters that we are remaining with. 7 letters would be competing for this. One of the 7 occupies that, we are left with 6, 5, 4, 3, 2, 1. Then this becomes our 7 factorial. It starts from 7, it goes to 1. This is 1 multiplied by 7 factorial multiplied by 1. 1 multiplied by 7 factorial multiplied by 1 gives us 5040. Meaning if the word starts with the letter E, ends with the letter S, those letters can be arranged in 5040 ways. The third question, third question says the second letter must be Q. The 7th letter must be an O. There are 2 positions again that are restricted. The second letter and the 7th letter. Letter C, 9 spaces again. 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 spaces. The second letter must be a Q, meaning here only a Q is going to occupy that position. The 7th letter must be an O. 1, 2, 3, 4, 5, 6, 7. That there must be an O. On the restricted position, because there is only 1 Q that is competing there and 1 O that competes there. On those positions, we are going to write 1, 1. There is 1 Q on the weight equation, hence 1. There is 1 O on the weight equation, hence 1 on the 7th position. Again, we are removing 2 letters. O is removed, Q is removed. We are left with 7 letters. 7 letters that are going to compete. 7 of them would compete for the first position. There would be 6, 5, 4, 3, 2, and 1. Now, product of descending natural numbers does not necessarily mean they must follow each other, because this is the product of descending natural numbers. 7, 6, 5, 4, 3, 2, 1. That is the product of our descending natural numbers. Meaning we can rewrite this as our 7 factorial multiplied by 1 of Q multiplied by 1 of O. 7 factorial is still the same answer as the one that we got from letter B, 5040. Meaning if letter Q occupies the second position, O occupies the 7th position, they can be rearranged in 5040 ways. Letter D. Letter D. Letter D says, let me erase this. Letter D. Letter D says the first letter must be a vowel. On the word equations, how many vowels do we have? We have E, U, A, I, O. We have all vowels on the word equations. All 5 of them are there. Vowels is R, A, E, O, U. All 5 of them are there, meaning we are going to have 9 spaces like we had initially, because there are 9 letters on the word equations. 1, 2, 3, 4, 5, 6, 7, 8, 9. Position 1, it must only be a vowel that competes there. It must only be a vowel because they say the letter, first letter must be a vowel. How many vowels do we have on the weight equations? We have 1, 2, 3, 4, 5. Meaning on position 1, all 5 of the vowels are going to compete there. But not all 5 of them would occupy that position. one vowel would compete or would occupy that, meaning the other vowels can occupy any other position. As long as it starts with a vowel, there is no problem because they're saying the first letter must be a vowel. Now, let's say letter E occupied that. It leaves us with 6 or it leaves us with 8 letters. If one vowel occupied, of the 9 letters, we remove just one. Meaning the second position, it would be 8. Then we have 7, 6, 5, 4, 3, 2, and 1. 5, 4, 3, 2, and 1. 2, 1. From 8 up to 1, it is the product of descending natural numbers. Meaning our answer would be 5 multiplied by 8 factorial. 5 multiplied by 8 factorial, it gives us 201,000. 201,600. Meaning, if the vowel must be the first letter, the letters of the word equations can be arranged in 201,600. 5 multiplied by 8 factorial. Letter E. The first and last letters must be a vowel. Letter E. 1, 2, 3, 4, 5, 6, 7, 8, 9. The first letter and the last letter must be a vowel. Now, we said whenever there is a position that is being restricted, we start first filling in the restricted positions, meaning we will start first filling the first position and then fill in the last position. Then with the remaining letters, we can fill in the remaining positions. Now, how many vowels do we have? We have 5 vowels that will be competing for the first position. One of the 5 vowels occupies that. It leaves us with 4 vowels for the last position. And then in between, we can have any other letter as long as the first and last are vowels. Meaning on the word equations now, we have removed 2 letters. Let's say it's A and U that are removed from the word equations. It leaves us with 7 letters. 1, 2, 3, 4, 5, 6, 7. It leaves us with 7 letters, meaning all 7 of them would compete for this position. One of the 7 occupies, leaves us with 6. Then we'll have 5 there, 4, 3, 2, and 1. Product of descending natural numbers from n to 1. It is called a factorial. Therefore, we'll have 5 multiplied by 7 factorial multiplied by 4. 5 multiplied by 7 factorial multiplied by 4. Then this gives us 100,800. Meaning they can be arranged in 100,800 if they are to start and end with a vowel. Let's check the other examples because we are not only dealing with identical letters. We can also have arrangements of objects that are identical. Now, whenever we have identical letters, okay, on this slide, that's where we had no identical letters in a word. A word that has no identical letters. These are the examples that we had for no identical letters in a word. But not all words are having, or not all words are having non-identical letters only. We can have a word that has identical letters. Now, when it comes to the identical letters, now we have n objects with identical letters, R, P, and K, can be arranged in n factorial, meaning that weight has how many letters, n being the total number of objects to be arranged, divided by R factorial, by P factorial, by K factorial. Now, these different letters that I have on the denominators would mean the number of identical objects are, you would have 3 of them if there are 3 identical objects in the weight, or 3 identical letters in a weight. P being the number of identical objects P, K being the number of identical objects K. Meaning if you have a weight that has identical objects, then that answer, or we are going to have a fraction in the number of different ways that can be rearranged. To accommodate for the identical letters, we then have our denominator. Now let's check the example that I have on the screen. It says, in how many ways, in how many different ways can the letters of the word Ubuntu be arranged? Ubuntu has how many letters? That would be your numerator. We check the letters of the word Ubuntu. Ubuntu has 1, 2, 3, 4, 5, 6. Ubuntu has 6 different letters, meaning the number of ways it can be rearranged is 6 factorial. This is for the word Ubuntu in total. Divided by, is there a letter on the word Ubuntu that appears more than once? If there is a letter, it appears how many times? Then we divide by that. On the word Ubuntu, U appears 3 times. Therefore, our answer would be 6 factorial divided by 3 factorial of the word U, or of the letter U that appears 3 times. This is the total number of ways, and this is the identical letter. The letter U appears 3 times. Then we'll have the arrangements that are 6 factorial divided by 3 factorial. And if you punch this in your calculator, 6 factorial divided by 3 factorial, it gives us 120, meaning the letters of the word Ubuntu can be arranged in 120 different ways. Now, with this, let us check the other examples now. With this, let us check the other examples that we have. With this, let us check the other examples that we have. Consider the word advertisement. Consider the word advertisement. Advertisement, if you check the number of words, the number of letters, basically, the number of letters that are in the word advertisement. Advertisement has 13 letters. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Advertisement has 13 letters. Let's check the first question, what it says. It says, how many word arrangements can be made with this word if repeated letters are treated as different letters, meaning that the word that appears more than once, it is now treated as different letters. There are 2 letters that are appearing more than once on the word advertisement. There is letter E that appears 3 times. There is letter T that appears 2 times. Now, those words or those letters, E and T, on the first example, it says they are treated as different letters. If they are treated as different letters, it means there is no fraction, because E1, E2, E3, that's where now they are different. Now, advertisement has 13 letters. 13 letters means we'll break 13 spaces. But because of the space that I have here for 3.1, 13 letters, 13 spaces, that means it would happen in 13 factorial ways. It will happen in 13 factorial ways. 13 factorial ways, then 3.2. How many word arrangements can be made with this weight if the repeated letters are treated as identical? Now, those words are no longer the same like it was on the first example. Repeated letters are in this case treated as identical. If they are treated as identical, then advertisement has 13 letters. That is 13 factorial divided by those identical letters. Which letter appears more than once here? E appears 1, 2, 3. Meaning on the word advertisement, we have 3 E's. That means we are going to divide by 3 factorial. Multiplied by, is E the only letter that appears more than once? If we check advertisement, also has letter T. T appears twice, meaning it would be 2 factorial for the letter T. Is there any other letter that appears there more than once? No. Meaning our answer to that question would be 13 factorial divided by 3 factorial by 2 factorial. Some answers would be a long sum on your calculator. If it gives you that long number, it's okay. You can leave your answer with factorials as it is. 3.3. 3.3, it says how many arrangements can be made with this word if the word starts and ends with the same letter. Starts and ends with the same letter. Advertisement, like I've said, has 13 letters. Let's create those 13 spaces here and check. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. For it to start and end with the same letter, it means that letter has to be appearing more than once on the word. And because there are 2 letters that are appearing more than once, it can either start with the letter E and with the letter E. It can either start with the letter E and end with the letter E. That is the same letter. But it is not only E that appears more than once. It can even have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Okay, it can also start with letter T and with letter T. But because we are not creating 2 words, it's either it's going to be this or it's going to be that. Meaning it's either it's going to end and start with letter E or it's going to start and end with letter T. Or in our probability means we are going to add the 2 possibilities. Possibility of ending and starting with E, we'll add it with possibility of starting and ending with a T. The repeated letters, there is E, 1 for the E's. It would be 1 here, 1 there. Meaning on the word advertisement, we no longer have 11 or 13 words. We are left with 11 letters. 11 letters that are now having for possibility number 1, where it starts and ends with letter E. It would be 11 because we have removed 2 E's. 11 factorial divided by, after removing the 2 E's on the word advertisement, is there a letter that appears more than once? It would be a T. Because E's, we had 3 E's. But after fixing 1 E on the first position, 1 E on the last position, it leaves us with 1 E. On the remaining letters, E does not repeat. The identical letter there now becomes letter T. Then it's 11 factorial divided by 2 factorial. These are the number of ways where it starts and ends with letter E. But it is not only that. It can even start and end with letter T. If it starts and ends with letter T, it would be 1 for the T there, 1 for a T there. Then it leaves us again with 11 ways or 11 letters that are remaining. That is 11 factorial divided by of the remaining letters, is there a letter that appears more than once? I think letter E appears 3 times. Then we divide by 3 factorial. Then our response for number 3.3 would be 11 factorial divided by 2 factorial plus, because it is not the only possibility that we have. It's either we have this or we have 11 factorial divided by 3 factorial. The first one is when it starts and ends with an E. The second one is when it starts and ends with the letter T. Then you can punch that in your calculator. It would give us the answer to that question. Now, moving right along, passwords, PIN codes, and numbers. Passwords, PIN codes, and numbers, which is the second last part of counting principles. Now, on the passwords, PIN codes, and numbers, here are the key things to note. Is a password or are the numbers allowed to repeat or not? If you can respond to that question, then the starting point, you have the perfect starting point. Are the numbers allowed to repeat or not? The second point, is there any position that is being restricted? If there is a position that is being restricted, we start at that restricted position. Okay, the third bullet, even numbered codes. This is now a restriction. The restrictions that we have.
I would connect,
would be
man,
in
as you
the
connect.
following. Even numbered codes. Even numbered codes are codes that are divisible by 2. Now, for a code to be an even numbered or divisible by 2, meaning this means that it ends, whatever that we have ends with an even number. Meaning that is a restriction. A code that is even numbered, meaning it ends with an even number, or a code that is divisible by 2, that code ends with an even number. The second restriction that we have is a code that is divisible by 5. For a code to be divisible by 5, irrespective of the digits that code has to end as well. It ends with a 0, it ends with 0 or 5. Meaning the restriction that we have, if it says a code that is divisible by 5, it means that code's the last position is the one that is being restricted. On the last position, it must only be a 0.
So what will
Sir, your mic is muted. Sir.
Okay, am I audible now?
Yes, sir.
Oh, thank you very much. Sorry for that. We will then check the examples. I think I just wrote without noticing that I'm not audible. Now I'll just go through what I've just written so that it can be clear for us moving forward when we are doing the examples. The restrictions that we have under the password codes and numbers, numbers that are on even numbered codes or codes that are divisible by 2. Being divisible by 2 restricts the last position to being an even number only. meaning the last position is restricted. It can only be an even number, including 0. Codes that are divisible by 5 restricts the last position. Last position, if it's divisible by 5, meaning it must end with a 0 or 5. Codes that are divisible by 10 restricts the last position. Last position must only be a 0. Any number that is ending with 0 would be divisible by 10. Now, the first position can also be restricted by the words greater than, less than. So those words are also restricting the first position. A code greater than 500, a code less than 600. If a code is less than 600, a 3-digit code that is less than 600, that code cannot start with 7, 8, or 9. Because any number, 3-digit number starting with those would be greater than 600. So on the restrictions under password, pin codes, and numbers, the first position can be restricted using the words greater than or less than. The last position can be restricted using the words divisible by 2, divisible by 5, divisible by 10, or even saying the code ends with a 9, where there is only one number that can occupy that. Now, having said that, let's check the examples that we have. The first example that I have, it says the number of digits, the number of digits in a code gives us the number of spaces that we are going to create. Remember when we were doing the arrangements or seating arrangements, we said the number of seats gives us the number of spaces that we are going to create. If 2 seats are being competed for by 8 people, we are only creating 2 seats. But here, the number of digits in a code that we are creating gives us the number of spaces that we are going to create. The example that I have here says a 4-digit code. A 4-digit code. We have the number of digits in that code. It is 4-digit codes, meaning that the number of spaces that you are going to create would be 4. Because we are creating a digit that only has 4 code, or we are creating a digit that has 4 code that has 4 digits. Now, let's check the first one. I'll respond to them here separately. 2.1. It says the statement, a 4-digit code not beginning with 0. This is the first restriction that we have. Whatever the code that you are going to create, it must not begin with 0. 0 is not going to compete for the first position, but it can compete going forward on the other 3 positions, are to be constructed from this set of digits. 1, 2, 3, 4, 5, 6, 7, 8, and 0. Please do not just assume that it is 0 up to 9. We use the digits that are given to us. If 9 is not given, that means 9 will not be competing for any of the positions. If 9 was given, then 9 would compete. In this instance, we are only given 9 numbers from 0 up to 8, excluding 9. Therefore, on the code that you are going to create, there won't be any 9 in that code. Now we are creating a 4-digit code. Number 1, how many 4-digit codes can be constructed if repetition of digits is allowed? Digits are allowed to repeat. That means there is a possibility of me having a code that says 1, 1, 1, 1. Meaning all the digits will be competing for all positions because they are allowed to repeat. Now we create 4 spaces. 1, 2, 3, 4. Now, how many codes will be competing for the first position? Remember, we have 9 digits that are competing for these 4 positions, but not beginning with 0. Meaning for the first position, 0 is excluded. Meaning only 8 numbers will be competing for the first position because we exclude 0. We would write 8 here for those 8 letters or those 8 numbers that will be competing for that position. But digits are allowed to repeat. For the second position going forward, 0 can compete. Meaning all 9 of them, because they are allowed to repeat, irrespective of which number occupied the first position, that number can compete again for the other positions going forward. Now, the second position, all 9 of them would compete for this. The third position, 9. The last position, 9. Therefore, our answer to this would be 8 multiplied by, this is not 9 factorial. This will now be 9 to the power of 3. 8 multiplied by 9 to the power of 3. 8 multiplied by 9 to the power of 3. That gives us the answer. 8 multiplied by 9 to the power of 3 gives us 5,832. 5,832. 8 multiplied by 9 to the power of 3. The second question, 2.2. 2.2 says, how many 4-digit codes can be constructed if repetition of digits is not allowed? Meaning a number is only allowed to compete for one position. Once that number occupies the position, it will not compete for the other position because it is not allowed to repeat. We still create our 4 spaces, 1, 2, 3, 4, because we are creating a 4-digit code. Remember, the first position, 0, is not allowed to compete for that. Now, the number of, the options that we have for position number 1 are 8, excluding 0. One of the 8 occupies this. Let's say that position is occupied by 8, meaning 8 is being removed from the numbers that we have. But 0, now we include 0 because 0 can compete from the second position going forward. From the 8 that we had, we are remaining with 7, plus that 1 of 0 that can compete for the positions going forward. Meaning the second position, it will now be competed for by 8 numbers. The first position, it was 8 because we excluded 0. One of the 8 occupies that, it leaves us with 7 numbers. Of the 7 numbers, we then add that 0 that we excluded for the first position. It gives us 8 numbers again. Then the third position of the 8, now we are left with 7 because numbers are not allowed to repeat. After that 7, we are left with 6. Then our response for the second one will be 8 multiplied by 8 multiplied by 7 multiplied by 6. Please be aware that this is not a factorial because it does not run from 8 up to 1. So you will write this as it is and then you multiply in between. That will give you 2,688. Meaning if the code is a 4-digit code, not beginning with 0 and repetition of digits is not allowed, then we can create 2,888 codes using the digits that are given to us. The third one talks about probability. The third one talks about probability, and we are going to do probability at a later stage. I will come back to the third one after dealing with probability. The third one will respond to it immediately after doing probability, because probability is this other part after here. This would be the last example before, or second last example before probability. Then we'll go back to respond to that question that required us to find the probability, because this question now says calculate the probability. So we'll have to address first the issue of probability on how we find the probability before attempting 2.3. I have this activity again that says, it's 3 questions. Given the digits 1, 2, 3, 4, 5, 6, 7, and or 8 and 9, meaning in total here we have 9 digits from 1 up to 9. Calculate how many unique 5-digit codes. 5-digit codes means we are going to create 5 spaces. Can be formed using the digits above if the first one, digits may be repeated, meaning a digit can be used more than once. We create 5 spaces for 1.1.1. 1, 2, 3, 4, 5. 5 spaces because we are creating a code that has 5 digits. The number of digits that we have here are 9 because it is from 1 up to 9. Therefore, all 9 of them would be competing for the first position. Any of the 9 can start. But because they said digits may be repeated, the second position would also be competed by 9 letters. The third one, 9 letters, 9 letters, 9 letters. Now, this becomes now 9 to the power of 5. This then becomes 9 to the power of 5. You punch that in the calculator, 9 to the power of 5 gives us 50. 9 to the power of 5 gives us 59,449. Also 59,049. 59,049. 1.2. 1.2 says digits may not be repeated. We are still creating 5-digit codes, but now digits are not allowed to repeat. We are creating 4 or 5 spaces, not 9 of the 9 digits that we have. 5 because of the digits that we create, codes, digits in a code that we're creating. We are creating a code that has 5 digits. Then it's 5 spaces. 1, 2, 3, 4, 5. All 9 of them would compete for the first position. One of the 9 occupies this, we are left with 8. One of the 8 occupies, we are left with 7, 6, and 5. Then we multiply in between. 9 multiplied by 8, multiplied by 7, multiplied by 6, multiplied by 5. That, when you punch it in the calculator, it would give us 15,120, meaning the number of codes that can be created there are 15,120. The third question, calculate how many 3-digit codes can be formed. 3-digit codes can be formed, meaning we are no longer creating 5 spaces. A code that you create now has 3 digits. For 1.3, we are having 3 spaces now. 1, 2, 3, because it is a 3-digit code. Number 1, they are saying digits may be repeated, meaning a number can be used many times. The second bullet says a code is greater than 400, but less than 600. Greater than, less than restricts the first position, meaning the first position is restricted by that. The code is divisible by 5. Divisible by 5 on this 3-digit code restricts the last position. Now let's check what competes on the restricted positions. On the digits that are given, 1 up to 9, for a 3-digit code to be greater than 400, less than 600, it cannot start with 1. Any 3-digit number that is starting with 1 is less than 400. It cannot start with 2 and 3. Meaning, on the first position, it can only be 4 and 5. It can't even start with 6 because they are saying it is less than 600. Any 3-digit number that you create that starts with 6, using the digits that we have, it would be greater than 600, of which we are looking for a code that is less than 600. Meaning the first position must only be 4 or 5. Last position is restricted by the third bullet. A code that is divisible by 5. We said a code that is divisible by 5 must end with 0 or 5. But looking at the digits that are given to us, we don't have 0 there, meaning it must only end with 5. Digits are allowed to repeat, meaning 5 can occupy the first position and the last position because it is allowed to repeat by the first bullet. The number of codes that are competing for the number of digits that are competing for the first position would be 2. It is only 5 and 4. The last position, it is only 5 for it to be divisible by 5. Only 5 is competing there because digits may be repeated. All 9 of them would be competing for the middle position. Meaning my answer would be 2 multiplied by 9 multiplied by 1. Meaning the number of codes that can be created here are 80. Meaning you can only create 18 codes under those 3 different conditions. Digits are repeated, the code is greater than 400 but less than 600, and the code is divisible by 5. Now, the last example that I have before we do probability. The digits 1 to 7 are used to create 4-digit code to enter a locked room. The number of digits in a code is 4, gives us the number of spaces, meaning we are going to create 4 spaces, 1, 2, 3, and 4. How many different codes are possible if the digits may not repeat? It is different compared to the previous example. The previous example, the digits were allowed to repeat, but in this example, the digits are not allowed to repeat. And the code must be an even number. Even number, we said it is divisible. Even number, we said for it to be an even number, it is divisible by 2. Even number divisible by 2. Even number divisible by 2, meaning this restricts the last position. Even number, last position. And bigger than 5,000. Bigger than 5,000 is the same as greater than 5,000, meaning it restricts the first position. Using the numbers 1, 2, 3, 4, 5, 6, and 7. Using these numbers, if a number is bigger than 5,000, that number can start with 1. Any 4-digit number that starts with 1 is less than 5,000, meaning 1 can start, 2 can start, 3 can't, 4 can't, but 5 can, meaning our position 1 can only be 5, 6, and 7. Any number that starts with 5 using the numbers that we have here would be greater than 5,000. 6 greater than 5,000. 7 greater than 5,000. The last position by the last position, it is restricted by that. The code must be an even number. What are the even numbers that we have on the numbers that are given to us? It can either be 2, 4, or 6. 2, 4, or 6. Now, the digits are not allowed to repeat. If there is a number that appears on 2 restricted positions and digits are not allowed to repeat, then it is advisable for us to do it separately. There is a number. There is 6 here, there is 6 there, and 6 cannot repeat because they said digits may not repeat, but 6 appears on 2 restricted positions. If you come across such case where a number appears on 2 restricted positions and digits are not allowed to repeat, then we do it separately. We either fix the first position or we fix the last position. Now, in this case, because the options that we have for the last and first are the same, usually we would say fix the one that has lesser options. But in this case, the first position, we have 3 options for it. The last position, we also have 3 options for it. So, anyhow, whichever way you fix. Now, we are going to fix the first position. By fixing the first position, this is what we mean. We say 1, 2, 3, 4. I fix 5 here. 1, 2, 3, 4. I fix 6 here. 1, 2, 3, 4. Then we fix 7 there. Meaning, I am saying to us, position 1, let it be 5 only. If 5 occupied the first position, there was no 5 on the last position. Meaning, all 3 of them would compete for that last position. Digits are not allowed to repeat. Of the 7 digits that we have, 2 is engaged. We have 1 on the first position, 1 on the last position. Meaning here we are left with 5 and then there 4. We fixed again the first position to be 6 only. 6, then we write 1. If 6 occupied the first position, 6 will not be competing for the last position because it cannot repeat. Meaning the last position will then be competed by 2 numbers, which is 2 and 4. Because I said 6 must occupy the first position, 6 is not allowed to repeat. 6 can occupy the first and last because it is not allowed to repeat. So I exclude it on the numbers that are competing for the last position. Meaning the last position would only be 2 and 4 that are competing. Then in the middle here we have 5 and 4. The last one I fix 7, meaning I will write 1. Once 7 occupies the first position, there is no 7 on the last position, meaning all 3 of them would compete. Then in between, I have 5 and 4. Then you multiply. Because you are not going to have all these options at the same time. It's either you're going to have this or you are going to have this, or you are going to have that. Then you multiply. 5 multiplied by 4 multiplied by 3. That gives us 60. Even here, it would be 60. Then we have 5 multiplied by 4 multiplied by 2. Here we have 40. Then you add your possible outcomes. 60 plus 40 plus 60. Then the total number of ways then would be 160, meaning the response to this question, the total number of digits that we can be creating that are codes that are greater than 5,000, and even number where digits are not allowed to repeat, we will be able to create 160 different codes. Left hand. Okay, now after this last example that we have, we can then address that question that needed us to find the probability. We can address the question that needed us to find the probability, which is 2.3. 2.3, which would be the last one, I think, for the day because of time. Now, this question says, calculate the probability of randomly constructing a 4-digit code, which is divisible by 5. Repetition of digits is allowed. Probability. Once it says probability, we know probability of event A is equals to number of possible outcomes over number of sample space. For the possible outcomes, you take into consideration the given restriction. What is the condition that is attached to the probability that you are looking for? Then you would get your number of possible outcomes. The condition is a code that is divisible by 5 and repetition is allowed. The repetition that is allowed would give us the sample space. Of the two questions, we have the total number of ways where repetition is allowed. We found it to be repetition allowed. We found it to be 5,832, meaning that becomes our sample space where repetition is allowed. But we are now left with finding the possible outcomes. Number of possible outcomes. Let's do it here. Number of possible outcomes. Remember, we are creating a 4-digit code. 1, 2, 3, 4, not beginning with 0. A code that is divisible by 5. Remember, divisible by 5 restricts the last position. Which numbers must occupy that for a code to be divisible by 5? It is only 0 and 5, meaning there are only 2 numbers that are going to compete for that position, which is 0 and 5. Because the digits are allowed to repeat after filling in the first position, all other numbers will be competing for the first, except for 0, because 0 is excluded based on that condition not beginning with 0. How many numbers will be competing for the first position? 8. Digits are allowed to repeat, irrespective of which numbers occupied the first and last. All 9 of them would compete here because it is that 8 plus the 0 because it is allowed to repeat. And then there would also have our 9. Meaning our total, our possible outcomes in this case, it would be 8 multiplied by 9, multiplied by 9, multiplied by 2. 8 multiplied by 9, multiplied by 9, multiplied by 2 gives us 1,296. This is our number of possible outcomes. Therefore, probability of that event, number of possible outcomes is 1,296 divided by the sample space. Sample space is you writing those code where repetition is allowed. And we had those 4-digit code if repetition is allowed. We had our sample space that would be 5,832. Then you divide the 2. 5,832, then it gives us the probability of 2/9. And remember, whenever you are calculating the probability has a scale from 0 up to 1. Anything greater than 1 or less than 0 will not be, or you'd have made a mistake there. So probability starts from 0, ends at 1. So this is how you approach a probability type of question. Thank you very much for your cooperation. We will meet again next week when we do preparations for paper 1 and paper 2. Please sign the attendance registers that have been circulated in the subject advisors WhatsApp group. Thank you very much. We will meet on the 2nd of September for paper 1 and paper 2 exam tips. Thank you very much.